Hello, and in this one we're going to look at a few more interesting cases of networks with poles and zeros in their responses. The first one to look at is this one. Now, we can analyse this one fairly readily. It is a potential divider. This time, the potential divider has a capacitor as its impedance up here. That's just 1 over j omega c in terms of its complex impedance. And the impedance of this element down here, where we're taking the output voltage of, this is a resistor in parallel with a capacitor. It's the same value of the capacitor up there, so that's convenient. I can just call this 1 over j omega c as well, and apply the general formula for the impedance of two components in parallel. That is, Z total equals the product of the impedances, R over j omega c in this case, divided by the sum of the impedances, R plus 1 over j omega c. So multiply top and bottom by j omega c, that just gives me R over 1 plus j omega rc. Put that into the potential divider equation, and I would get the gain as a function of frequency, which is the frequency response, h of omega, is the impedance of this term here, R over 1 plus j omega rc, divided by the total impedance in the potential divider, plus 1 over j omega c. Here, I'm going to try and get this into our standard form, or at least in terms of a polynomial on the top divided by a polynomial on the bottom. So if I have a term like this with 1 over something on the top or the bottom, I'm going to multiply by this denominator of this term. Do the same thing with the denominator of this term up here. So I'm going to multiply everything by j omega c times 1 plus j omega rc to get rid of these terms on the bottom. That would give me j omega rc over j omega rc plus 1 plus j omega rc. In other words, j omega rc over 1 plus 2 j omega rc. So, I can see that there is one zero, and my 1 0 is going to be at 0 hertz, because that's the value of j omega that would make the numerator equal to 0. I've got one pole, and my one pole would be at minus 1 over 2 rc, because that's the value of j omega that would make the denominator equal 0. So, I have a 0 at 0 hertz, and a pole at minus 1 over 2 rc, radians per second. I'm working with omegas, radians per second at the moment. Why is this an interesting case? Well, it's an interesting case because of the second question on the slide. What is the response at infinite frequencies? Looking at the frequency response, you might say, well, if omega is infinite, then we can neglect this plus 1 term on the bottom here, because this term is going to be so much bigger than the 1. So we can neglect the 1. Everything cancels except for the factor of 2 on the bottom, and we can say that the frequency response at an infinite frequency is just a half. Which is right, except if you have a look at the circuit and say, well, at infinite frequencies, the impedance of a capacitor is 0. Therefore, if I drew out the circuit, replacing the capacitors with 0 ohm resistors or just wires, we would see something like this. And we've got a contradiction. The voltage source is forcing this node here to be an oscillation with an amplitude of 1 volt. But this node here is also tied directly to ground, so it must be at ground all the time. This circuit cannot exist. And the problem here is to do with this idea of infinite frequency. You can never get to an infinite frequency. The capacitors will never have a absolutely zero impedance. This just means that at very, very high frequencies, a long way above the break frequencies of the zeros and the poles, the frequency response of this circuit is going to be a half. The output will be half the input, and in phase with it. Finally, we'll look at this one. Again, we can analyze it using the potential divider equation. We would just end up with h of omega equals the complex impedance of the component down here, which is 1 over j omega c, divided by the total complex impedance of all of the terms in the circuit. Multiply up by j omega c to get the top and the bottom in the form of polynomials. We would just get 1 over 1 plus j omega cr plus j omega squared L times c. Now, clearly there are no zeros. There are no values of j omega for which the numerator is 0. But the denominator is a quadratic in j omega. Quadratics have two roots, so there will be two poles, two values of j omega for which the denominator is 0. And we can work out where they are by solving the quadratic equation. In this case, that would just give us that j omega equals minus b, minus cr in this case, plus or minus the square root of b squared, c squared r squared, minus 4 times a, lc, times c, 1, all over 2a, 2lc. I can simplify this slightly by dividing through everything by c, and that would give me minus r over 2l, plus or minus the square root of the square of r squared minus 4 l over c all over 2l. Now, it would be perfectly possible to pick values of resistors, inductors, and capacitors so that r squared was less than 4l over c. In other words, r squared minus 4l over c is negative, and we'd have to take the square root of a negative number, and that would give us an imaginary result. That would suggest that our poles are complex. They have an imaginary component as well as a real component. Can this happen? Yes, it can, and it often does. Zeros and poles can be complex numbers as well as real numbers. And we'll be looking at complex poles and zeros a lot more in future videos. In fact, in the next video, I want to talk a little bit more about what a complex pole or a complex zero actually means, and introduce the rather head-scratching topic of imaginary and complex frequencies.